So this final example is going to be the magnetic force on an entire wire. So up until now, we've talked about the magnetic force on just a single particle. But now if it can apply a force on one moving particle, then it can apply a force on an entire wire full of moving particles. So that's what this new formula is about. The formula is given at the top there. I stands for the current of the wire. That's going to be measured in amps. And B is the magnetic field. L is how long the wire is in meters for the SI units. And the sine of theta is going to be the angle between the current and the magnetic field. So this, up until now, it's been 90 degrees the whole time. I'm usually going to use 90 degrees, but for this one example, I thought we'd see what happens if it's not 90 degrees. That just means we keep that sine theta term. So it'll be sine of 60 degrees in this case. So all you do is you multiply things. So the force, the magnitude of it will be IBL sine theta. So once again, for this unit, we're going to relax our rigor in terms of drawing the harpoons all the time and drawing the magnitude bars all the time, just because there's a whole lot of them. And so instead of doing magnitude of a vector, we'll just not put the vector arrow at all and not put the magnitude bars. So this equation I've written down here is all magnitudes here. So I'll just simply put in the values, 1.5 amps. The magnetic field is given. The length of the wire is 10 centimeters, which needs to be put into SI units of 0.1 meters. And then this time, they're at an angle to each other, so I'm going to keep the sine term. It'll be sine of 60. So I'm just multiplying all those out. So I'm getting 6 times 10 to the negative 5. Oh, I didn't do the sine 60 yet, I don't think. All right, so I'm getting 5 times 10 to the negative 5. It's going to be the one significant digit because the magnetic field was only expressed as one significant digit. So that's the magnitude of the force. The direction needs to be figured out by right-hand rule number 3, which I cut and paste that diagram on the left there. So the index finger is going to be the direction of the current, which is to the right. The middle finger is going to be the direction of the magnetic field, which is at a 60-degree angle. So this time your index and middle fingers are not 90 degrees to each other, they're 60 degrees to each other. However, your thumb still needs to be 90 degrees to both of your other two fingers. So when I make that 60-degree angle with my index and middle finger, put down my pencil so I can do it, I stick my thumb out. My thumb is sticking out of the page, and hopefully yours is too. So I'm just going to write a final statement here. A force as a vector is 5 times negative 5 newtons out of the page. So you might have seen the demonstrations from lesson 2 where they made the wires jump. They had the wires in a strong magnetic field, the wires jumped. So if this were happening here, the wire would jump out of the page at you if it were a real thing.